discuss for the semester is relativistic electrodynamics. And as you know, the theory of relativity, special relativity in particular, is intimately related to the theory of electricity and magnetism because of the fact that Maxwell's equations has this thing called the speed of light. And the mystery of what reference frame the speed of light was the speed c in was caused great confusion and all kind of machinations for decades to try to make sense of that. And as we all know now, and it's commonplace knowledge, the speed of light is the speed of light in all reference frames. And so today what I want to do is just very quickly review relativistic dynamics so that we can get to the subject of relativistic electrodynamics pretty rapidly, okay? How many of you have seen, just out of curiosity, I don't know what's covered in a lot of undergraduate courses, how many of you have seen in your undergraduate classes the theory of say, four vectors and Lorentz transformations and Lorentz invariants, covariant, contravariant notation, that kind of thing? So most of you, or maybe half, it's hard to know. We'll talk about that. Again, that's really what we're going to talk about next week. Okay, and its relationship to electricity and magnetism. All right, so let's get started. Of course, so the key point is that the speed of light is the same in all reference frames. This, together with the assumption that physics is the same in all inertial frames, is all we need to get everything about special relativity. All right. So, the idea is that if I imagine a reference frame, S, and if at the origin a spherical wave is emitted, electromagnetic wave in vacuum, and if there is a co-moving frame, S prime, moving at any other velocity, v, that say crosses, let's just say they synchronize such that at the origin, the light pulse goes off at the origin of this reference frame, then from the point of view of this co-moving observer, that spherical wave is being emanated at the speed of light from its origin, and it can't catch up to that wave crest or fall behind that wave crest. It will look exactly the same. Okay? So, if we look at a spherical wavefront, then all of the points on that spherical wavefront occur at positions x, y, and z such that that equals the time it takes for light to go that distance, ct, okay? So all of these points corresponding to at these times and these spatial coordinates correspond to some radius from the origin. this is in reference frame S, and the point here is that this must be true in the co-moving frame as well. So if there are coordinates x, y, and z in that co-moving frame S prime, then this has to equal Ct prime, quantity squared. And the only way this can be true is if time is different in the two reference frames. Okay. So the invariance of the speed of light insists that when we go to a co-moving frame, we not only change the spatial coordinates that describe events, but we must change the time coordinate. And the transformation that keeps this true, makes this true, is the Lorentz transformation. In particular, what we call Lorentz boost. Okay? So if we look at the specific example where the boost is along the x coordinate, by speed v, then we have the well-known Lorentz transformation that the x coordinate transforms according to x minus vt with the relativistic factor gamma, and t must also transform. And since we've made the boost along x, the y and z coordinates are unchanged, where gamma is the relativistic factor, which goes between 1 and infinity as v goes from 0 to the speed of light. Okay? Well known. Quick immediate consequences that we see from Lorentz transformations is we can ask the question about how do velocities add? That is to say, what speed will I see in a co-moving frame of some moving object or moving event relative to some lab frame? Okay. So, the velocity addition rule easily follows from a Lorentz transformation. So if, let us suppose that u is the limit as delta t goes to 0 of delta x delta t is this speed between or speed, how shall I put this? Speed associated with motion between two events. So let me emphasize what I mean by event. As you know, in relativity, when we want to talk about the coordinates, we include not only the spatial coordinates, but the temporal coordinates, and we call that an event. So an event happens at a particular time and with a particular set of spatial coordinates. So those are the space-time coordinates, what I'm calling an event. It happens at that time, at that position. So if I now want to go, so this is the speed associated with motion between two events that are separated by positions delta x, could be, well, it doesn't really matter, let's say we're along the co-moving direction x, with time separation between those events delta t. We take the limit That gives us the instantaneous speed between two events in frame S. So in frame S prime, U prime is equal to the limit delta x prime goes to 0, delta x prime over delta t prime. But we have transformations according to Lorentz transformations, how the x coordinates and t coordinates transform. So we're assuming that we're boosting, this is in frame S prime, boosted along x, which is the direction of the speed of the object in the initial reference frame. And that speed then is gamma delta x minus v delta t divided by gamma delta t minus v over c squared delta x equals the limit delta x goes to 0, delta x over delta t minus v over 1 minus v over c squared delta x delta t, having just divided everything by delta t, which says that the speed in the new reference frame is u minus v over 1 minus uv c squared. The velocity addition rule, familiar in special relativity. So in particular, for example, if the two events are separated by something moving at the speed of light, that's to say, if the event is the motion of that spherical wavefront, so that u equals c, well then u prime is c minus v, which is what you would have in Galilean relativity. If you're co-moving, you'd catch up, but normalized by this factor u is c v over c squared, which is equal to c. Right? Because I could cancel out the c, multiply everything by c, and I got c. So as we see, it's c. The speed of light is the same in all reference frames. Other quick factoids to remind you. Of course, we have the whole business of simultaneity. As you know, every paradox in relativity, you know, putting the ladder through the barn door and all of that, are all about the problems that our intuition is that if two events happen at the same time in our reference frame, they happen at the same time in all reference frames. But the fact of the matter is they don't. So two events that are simultaneous in one reference frame happen at different times in a co-moving frame. And that's trivial to see, that if I have two events, say that happen at position xa and some time t, and another position, but at the same time, that if I look at t b prime minus t a prime, the difference between the times of those events in the co-moving frame, that's equal to gamma tb minus ta minus v squared over, or v over c squared xb minus xa. These are the same, but if these x coordinates are different, then this time is not 0. These two times are separated. So events that are simultaneous in one reference frame are not going to be simultaneous in another reference frame. And every paradox in special relativity is always about that. You know, the barn didn't close at the same time. First, the first part of the ladder went in, and then the second one, and all that kind of stuff. Right. Time dilation. What do we mean by time dilation? What we mean is that, let's suppose we have two reference frames which are co-moving along their x directions. And let's say that there is a clock moving along with this speed. Okay? So there's a clock. In the rest frame of the clock, let me say it this way. The time interval between two ticks of the clock in the clock's reference frame, the clock's rest frame, occur at the same position. Right? So we don't have ticks, but here they are. As I'm moving along, as far as I'm concerned, this is happening at the same position in my frame. Okay? Relative to you, it's moving. So those two events in the S prime frame happen at some position xa, we'll call that x times ta. This is in the moving frame, so we'll call that prime. Moving with respect to you guys, not with respect to me, and the clock. So that's one, the clock goes tick and then it goes tick again. But at the same position. Okay? So the time interval between those two ticks in this frame is TB minus TA. Now we can ask, what is the time in the lab frame or the classroom frame? To do that, I boost backwards, or you boost you backwards. Oh, there you go. Bye. You're going backwards, so we boost you in that direction. Gamma. So delta t is equal to TB minus TA, which is gamma TB prime minus TA prime, plus V over C squared XB prime minus XA prime. Okay? but these happen at the same position relative to the clock's reference frame. So this is 0. So that means that the time between ticks that you see as the clock is passing by your eyes, moving at the speed v, those ticks are happening with a longer time interval, because gamma is always bigger than 1. So delta t is bigger than delta t prime. The moving clock ticks more slowly. Okay? The time between ticks in the clock's own reference frame is known as, so where is that? So this is time between ticks in clock's own reference frame is known as the propre time, which in French is your own. But sadly, it got translated into English as the proper time, which gives a totally wrong connotation, because it has nothing to do with, you know, being prim and proper or the correct time. Proper means propre, your own time, the time you see in your reference frame if you are the clock. Okay? So that's what's known as, what's referred to as the proper time. But it's not proper in the sense of correct at all. Okay? Very confusing. People say, well, that's the proper time. I want to use the proper time because I'm a proper kind of person. Okay, so of course we also have length contraction. So if I have now a ruler that has some length in its own rest frame, I want to know what is the length of that ruler seen in it as by me as it's moving by with some velocity v. Okay? So what we mean by the length is what is the spatial distance between these two ends at the same time in my frame. So that's what we mean by the length. The length, so if this is xb and this is xa, this is xb minus xa when tb equals ta. So in my reference frame, little explosion goes off at the same time, and then I ask what is the spatial distance between those 2 points. Okay? Now, of course, the ruler is moving by. So now the question we ask ourselves is, what is the length of the ruler in its own reference frame, co-moving with the ruler at L? I mean at V, pardon me. So, so now we boost by speed v along x. In that reference frame, the ruler is at rest. So this L is the L of the moving ruler. The ruler's moving by at speed v, and I ask what is this distance between these two events that happen at the same time. And now I want to know what is xb, so the length of the ruler when it is at rest is now, the way I've defined things, the distance between those 2 points, which don't happen at the same time, relative to what's going on in the ruler. So this then is equal to, let's just call this G equals T, gamma xb minus xa minus v tb minus ta. This is 0 because those events happen at the same time. That's how I define the length of the moving ruler. This is the rest frame length of the ruler. No, this is the moving, yes. And thus we see that the length of the moving ruler is the length of the ruler at rest divided by gamma. The length is contracted. Okay? So these, if the ruler was an inch, it would be an inch divided by gamma as seen by me if the explosions go off at the same time. All right?
Wait. Gamma is less than 1, isn't it?
No, gamma is always bigger than 1. No, you're thinking about beta. Beta is, gamma is defined there. There's gamma.
That's 1 minus beta squared.
So, again, look at gamma. It's in the coordinate.
Yeah.
Gamma is always, can be, when v goes to c, this goes to infinity. Thinking of beta. All right. So, right. So those are the very basics. We formalize this a little bit into thinking about the geometry space-time, which we'll talk about in some more detail next week. But let me just say a few words now. So the way we formalize this is that we define the event coordinates as a vector in a 4-dimensional space. So we define now a 4 vector, the space-time coordinates, which range from 0 to 3, where x0 is ct, x1 is the x coordinate, x2 is the y coordinate, and x3 is the z coordinate. Now, as you may have seen before, and we'll review some more, there's method to the madness of upper and lower subscripts. This actually means something. These are so-called the coordinates that are contravariant as opposed to covariant, and we'll review what the heck that actually means next Tuesday. For now, we'll just leave this as it is. So a Lorentz transformation is a linear transformation on the space-time coordinates. So if I do a boost, then the coordinates in the boosted reference frame are related to the coordinates in the unboosted frame through a matrix transformation using the lovely Einstein summation convention, where repeated indices are summed from 0 to 3. Okay? And you always sum an upper index with a lower index. The matrix here, this is a 4x4 matrix. That is, say, these are the elements of a 4x4 matrix, where for a boost along X, the matrix looks like this. Where gamma is 1 over the square root of 1 minus beta squared, and beta is v over 2. And this has okay. So we have a Lorentz transformation. All right. Now, one of the things that we see, very important fact that we note is that as derived in some sense by the whole assumptions of relativity, c squared equals x squared plus y squared plus v squared is invariant. Under a Lorentz transformation. In fact, that's how we just defined the Lorentz transformation. It was the transformation on the space-time coordinates that kept these things equal. Right? Which means that c squared minus x dot x equals 0, or that difference, the difference between this and this, which we'll call s squared, is invariant. It's a Lorentz invariant. Now, in particular, well, let me say a few things before I get to that. This leads us to define the norm of the 4 vector. So I define the norm squared, say, of the 4 vector x as x0 squared minus x1 squared plus x2 squared plus x3 squared, or x0 squared minus x squared. Because that norm is invariant under a Lorentz transformation. And we define this with that summation convention, with one of the coordinates up and one of the coordinates down, such that I put a minus sign on the spatial coordinates. So it's not the Euclidean norm. Which, of course, in Euclidean space, you take the sums of the squares of the coordinates. Here, some of those have negative signs in it. This is a Minkowski norm for Minkowski space. All right, so the key point here is that we defined the Lorentz transformation as the transformation on the coordinates that kept that norm the same in all reference frames. So the Lorentz transformation keeps the norm of the four vector of space-time the same in all reference frames. Yeah.
So it seems like when we like at least define the Lorentz transformation as the thing that kept that invariant, we only did that for light-like intervals. So how does that like follow for like intervals that aren't?
Well, it's true for all. So it's true if this is 0, so we're just about to define those intervals, well then it's 0 in all. But we can just check that in fact the Lorentz transformation keeps this difference the same no matter whether it's positive, negative, or 0.
Okay.
So we defined it for the case in some sense. I didn't really derive it, I just threw it out there. I motivated it by the transformation that kept the speed of light the same in all reference frames, which means that it keeps that interval 0 in all reference frames. But then it follows that that same transformation keeps this interval the same no matter whether it's positive, negative, or 0. So let's emphasize that point. Let's go to the next area. That's a very important fact. Because we just said that delta S was Lorentz invariant and C is Lorentz invariant, so the proper time is Lorentz invariant. Which means that if there are two events that occur, here they are, if delta t is the time interval between these two events in this reference frame, watching this particle move in space and time, then that time interval is related to the time interval, well, that's not exactly true. Let's take the limit as delta t goes to 0. Otherwise, I'd have to worry about the fact that the velocity could be changing. Because, of course, at every instance of time, I need to boost into a different reference frame to be in the instantaneous rest frame of the particle, unless the particle is moving at a constant speed. So for a small delta t, what we see is that the delta t in the lab frame is equal to gamma at the instantaneous velocity delta tau as delta tau goes to 0. And u is the instantaneous speed. So what we see from this is that delta tau, which is whatever the time interval is between those events divided by the local gamma, is Lorentz invariant. The time difference between two events is not Lorentz invariant. space and time transform into one another. But if I normalize it by the instantaneous speed, and if the speed between those two events was constant, then it wouldn't matter. But if I change that by gamma, then that combination, that ratio, is Lorentz invariant. Because the proper time is just proportional to that Lorentz invariant interval. You can check that. What you need to do is, you go to a different reference frame, change delta t, then of course you have to change u according to the velocity addition rule, plug it in, and it works. All right. So that's space-time as a four vector, the Lorentz invariant. You can define any other collection. So a general four vector is defined such that under a Lorentz transformation, the coordinates of that vector transform according to the same Lorentz transformation. Moreover, the norm of that vector squared is equal, by definition, to the same norm that we define for space and time. So we have, our four vectors are generally written as they have a time-like component and then three spatial components. That's how one typically would write a four vector. All right, so for example, we can have the four velocity. So if I look at space-time, and I want to look at the four velocity, how would I define it? Well, note the derivative of this with respect to the time coordinate is not a four vector. Why? Well, this is not going to transform in this manner, because the denominator transforms, and the numerator transforms, and the ratio transforms differently. So that's not a four vector. However, the proper time is a scalar, is invariant under a Lorentz transformation. So however, if I define u nu is equal to dx nu with respect to the proper time, then that is a four vector. Because this x transforms as a four vector, and this does nothing. It's invariant. Therefore, the ratio of them transforms like this. And as we just discussed, this is equal to gamma dx nu dt. where u is equal to dx dt, the instantaneous speed. That's what we just wrote over here. Okay, so that tells me that the forward velocity is equal to gamma d by dt of ct x, or gamma c gamma u. All right? So, now we can ask ourselves, what is the norm squared of this 4 vector? That's equal to the time component squared minus the spatial component, norm squared. But that's equal to gamma squared, which is 1 over u squared c squared, times c squared minus u squared, which is equal to c squared. So as expected, the norm of the forward vector is Lorentz invariant, as it must be. All right. Another example, the form momentum. So we define P nu is equal to the rest mass times the form velocity. And the rest mass is just a number, it's a Lorentz scalar. Thus, P nu is a 4 vector. And that equals m gamma c gamma n u. We call the spatial component of this the relativistic momentum. Okay? And sometimes we call the ratio or the multiplication of the rest mass by the relativistic gamma, if it's moving at speed u, as the relativistic mass. The mass, in some sense, increases. So the momentum is not just the rest mass times speed, but the increased mass times speed. Okay? Well, so what is our norm of the vector squared? Well, that's just going to be the mass times c squared. So we just had this was m times this, the norm squared of that was c squared, so the norm is m squared c squared. And that's a constant, which is the rest energy squared over c squared. All right, so if we write this out, the norm squared of the form momentum is equal to gamma squared m squared, well, let me write it this way. P0 squared minus P relativistic squared is equal to mc squared squared over c squared. Okay, so that means that c squared times p0 squared is equal to mc squared squared plus the relativistic momentum c squared, which we call the energy of the particle squared. So the energy of the particle is the rest energy squared and the motional energy squared. We can double check this, that this in fact makes sense, by plugging in and look at the non-relativistic limit of this. So P0, we said over here, was equal to gamma. So this is gamma squared m squared c to the fourth. Okay, so what we want to check, what I claim is that the energy, E, is equal to gamma mc squared, where instead of just having the rest mass, I have the relativistic mass. Plugging that in, that's gamma is 1 minus u over u squared over c squared to the minus 1/2 power times mc squared. For non-relativistic, u much, much less than c, E is approximately equal to, well, I can do a Taylor series expansion. And get, oh, there's a minus 1/2, that becomes a plus. So that is then mc squared plus 1/2 mv squared, which is the kinetic energy and the rest mass. So what the takeaway message here is that the form momentum is really the energy momentum for a vector. And that's P nu is equal to the energy over C, P relativistic. Where the norm squared is just the mass squared in units. So we have the famous equation that E squared equals MC squared plus PC squared. I used to always argue with my dad, and my dad loved to argue with me about physics. My dad was a dentist, but he loved to argue with me about physics. And he said, every time I came home from college, he would say, all right, now E equals MC squared, but photons have no mass. So that would mean their energy is 0. So physics is wrong. Well, that's you read the Time Magazine version. It's not equals MC squared, there's this other thing called PC that will never work. fight. I'm going to drill your tooth. So. All right. Let's see. Final thing I want to discuss today, which is force and dynamics. So, note again, if I look at the time derivative of the form momentum with respect, or the derivative of the form momentum with respect to time is not a force vector. So we define a force vector, which is called the Minkowski force, typically denoted as K, as a derivative of the momentum with respect to the proper time, or the rest mass times the acceleration as defined as U. I got mu. Mu's and mu's, let's call it nu. Okay? Which is equal to gamma m. So that is equal to, according to this, T. K mu is gamma d E dt over C, and gamma dp relativistic dt. Okay? And this is equal to gamma dp mu dt. Plugging in this. All right? This is what we call, in Newtonian physics, the force. The rate of change of the momentum with time. So what is the zero component
Power.
mean? Sorry?
Is that power?
It's related to that, so let's take a look at that. So note, we said that the norm squared of the forward velocity was a constant, c squared. That means if I take the derivative of this with respect to the proper time, this is 0. Doesn't matter if I write it. I mean, it's going to be this plus the other way around, but then I can raise and lower the indices back. So that means that if I multiply this by the rest mass, that the inner product between the Minkowski force and the forward velocity is 0. But we just learned how to take inner products and multiply their time-like components. So this is going to be K0, U0 minus K dot gamma U, which is equal to, let's see what we got here. We got gamma squared times the EDT, the derivative of the energy with respect to time, minus gamma squared force dotted into the kinematic velocity is equal to 0. So as was suggested, the EDT is F dot V, or F dot U in this case, I'm calling this local speed U, which is the rate at which work is done on particle. Okay, so I want to conclude with one last point about this. So what we have here, the Minkowski force, is often written as gamma times the force dotted into the local speed and gamma force. This is the time-like component, the space-like component of the Minkowski force. Okay, so for next lecture I want to derive one last fact. Let's consider the relationship between the force on a particle in its instantaneous rest frame and the lab. Okay, so what we have is some situation where we have a particle moving in space and time, and it's got some instantaneous speed u relative to the lab frame. And there is a force that we know is being exerted on this particle, and we want to relate that to the force seen by the particle in its own reference frame, okay, sitting on the spaceship that's trucking along with the particle. So let's quickly do that. Wait. All right, so in the boosted frame, which is the rest frame of the particle, well, the speed is 0. We're in the rest frame of the particle. So in that frame, gamma is 1, u is 0. So this is equal to that. In the lab frame, this is this. Okay? But we can relate these guys by the Lorentz transformation. So if we go into the lab frame, boost backwards, gamma f is equal to gamma, so I should write this way, k is equal to gamma k prime, because k0 is 0. This is k, we said was gamma f, and this is gamma f prime. So that tells me that f equals f prime. Well, that's only true if the boost was along the same direction as the force. Because, I should probably delay this because this is going to be more complicated to explain. Let me pick this up again. We don't really have the time. Let's finish this discussion next